This video is brought to you by mywayteaching.com.
So in this part, we are going to study about the potential energy of a spring. See, the spring force is an example of a variable force, and that was conservative too, isn't it? So now you can see a figure which is shown here. Okay, block attached to a spring. You can see here a block which is attached to a spring and resting on a smooth horizontal surface, isn't it? And the other end of the spring is attached to the rigid wall. Okay, the other end of the spring is attached to the rigid wall. So the spring is light and it may be treated as massless. So in an ideal spring, the spring force Fs is proportional to x, where x is the displacement of this block from the equilibrium position. Okay, so the displacement could be positive or negative. You can see here from the equilibrium position in this figure B, it is the displacement is positive, and here from the equilibrium position in the third case, the displacement is negative, isn't it? So this force law for the spring, that is called as Hooke's law. So mathematically, we'll write that law as Fs is equal to minus k x. Okay, so where constant k is called a spring constant, and the unit of this k is given by Newton per meter. Okay, so the spring is said to be stiff if k is large. Otherwise, if k is very small, then the spring will be very soft. Suppose we pull a block outwards, as you see in figure B, like x is positive. If you pull the block in that direction, if the extension is xm, okay, then the work done by the spring force is given by, okay, if the extension is xm, when we pull the block outwards, okay, then the work done by the spring force is given by ws. So we can write it as the 0 to xm integration of 0 to xm fs dx. Okay, so that one we can write it as 0 to xm. We know the spring force is nothing but kx. Okay, so if you differentiate it, x is the differentiation of x is x square. In this case, it is xm square by 2. So this expression may also be obtained by considering the area of triangle. Okay. So the work done by the external pulling force F is positive since it overcomes the spring force. Okay. See, the same is true when spring is compressed with the displacement. So that also we saw how it is compressed, isn't it? In the third case, okay, the spring force does work ws is equal to minus kxc square by 2 when it is compressed. So while the external force F does work of positive kxc square by 2. If the block is moved from an initial displacement xi to the final displacement xf, the work done by the spring force is given by, if the block is moved from the initial position xi to the final position xf. In that particular case, okay, the work done by the spring force is given by ws is equal to minus of xi to xf kx dx. Okay, that is nothing but kx square by 2. First is xi minus kxf square by 2. Okay, thus the work done by the spring force, it depends only on the endpoints. Specifically, if the block is pulled from xi and allowed to return to xi. Okay, in that case, the work done will be 0 because there is no displacement, isn't it? The block is pulled from xi, again it is allowed to return to xi. So that is given by kxi square by 2 minus of k xi square by 2, that is equal to 0. So the work done by the spring force in a cyclic process is 0. So we have explicitly demonstrated that the spring force is position dependent only as first stated by Hooke. Okay, the spring force is what? It is position dependent. So that is the first conclusion. And the second is the spring force does work with only depends on the initial and final positions. So we can say the spring force is a conservative force because it depends only on the initial and final points. Okay, so we define potential energy of the spring to be zero when block and spring system both are in equilibrium position. For an extension x, the above for the okay compression, it suggests that the potential energy will be minus, okay, the potential energy will be kx square by 2. Okay, so you may easily verify that the variation of this potential energy, that is nothing but minus dv by dx, is equal to minus kx. Okay, the spring force, if the block of mass m is extended to xm and it is released from rest, then its total mechanical energy at any arbitrary point x, where x lies between minus xm to plus xm, is given by its total mechanical energy. It's given by half k into xm square minus half kx square plus half mv square. Okay, so where we have invoked the conservation of mechanical energy. Okay, this suggests that the speed as well as kinetic energy, they both will be maximum at the equilibrium position, that is when x is equal to 0. So we can write it as 1 by 2 m vm square is equal to 1 by 2 k xm square. Okay, where Vm is maximum speed, that is given by Vm is maximum speed. So that is given by k by m into xm. Okay. So this k by m has the dimensions of t square, and equation is dimensionally correct. The kinetic energy gets converted into potential energy and vice versa. So, and the total mechanical energy remains constant. So, we can see graphically all those things in the figure. Okay. And here in the case where you can see in this particular figure, so it is the plot of Fs, that is the spring force, isn't it? Fs matlab Fs means it is the spring force. Okay. The area of the shaded triangle, it represents the work done by the spring force, and due to the opposing signs of Fs as well as X, the work done is negative. Okay.